In this next clip, we return to the particle wave duality, and we just looked at electrons, which are particles and discrete. This is the classical picture. And by contrast, we have best example of a wave for us will be light. Light is a wave and continuous. And again, this is the classical picture. Here we have a picture of a wave, a classic wave. It has an amplitude, how high it goes. At the highest point, the crest. The lowest point, the trough. And the distance between crests is the wavelength, which goes by the Greek letter lambda, which is the Greek letter L. In addition to amplitude and lambda, waves can travel. Here's a movie of them traveling. You can see the wave is going left or right, and when they travel, both their amplitude and their lambda do not change. Okay, so that's the velocity. V. And now we have one more important concept for the waves, which is the frequency. First, just let me get some Greek out of the way. It goes by the letter nu. Nu is the Greek letter N. And if you look at the letter N, and if you just look at this part of it, that is the Greek letter nu. So what is frequency? Frequency is in per second, and it's how many times the wave that's traveling reaches a certain point. In this picture, both these waves will be moving at the same velocity, and they'll be moving to the left. And see which one reaches, the crest reaches the endpoint more often, the one on the top or the one on the bottom. So put in chat, once I turn on the movie, which one has the higher frequency. It reaches the endpoint on the left more often. Here's the movie. So put it in chat. And so what you see is that the top picture, so the velocity was constant, and the top picture, nu was greater, and at the same time in the top picture, lambda was, just put in chat, bigger or smaller, put in chat. Lambda was smaller. And that's because of this classic relationship, true for all waves, that velocity, this is a v, not a nu, is always equal to nu, the frequency, times lambda. The most classic, famous example of that is the speed of light, which is a velocity, which goes by the letter c, is equal to the frequency of light times its wavelength. Light is so important. We have names for all the frequencies and wavelengths. The visible light, the one with the shortest wavelength, is called violet. The one with the longest wavelength is called red. Even shorter than wavelength, we can't see them, are X-rays and UV. Even longer wavelengths, again, we can't see them, are infrared, IR, and microwave. So we have names for all of these. And one more thing. In addition to waves that move left or right, waves can add. And if we add the wave that's moving to the left and the wave that's moving to the right, which you'll see in a second, we're going to add them together. Something amazing happens. You'll see this in this movie. I find it totally unexpected. You end up getting a wave with the same wavelength, but which isn't traveling. and that is called a standing wave. So waves can add, and they add or they cancel out. It's called in phase or out of phase, constructive or destructive interference, and they lead to the most beautiful property, which is called diffraction. Here are two water waves, and you can see where it's very bright, the waves are adding together a lot, and then when it's very dark, they're canceling each other out because they're out of phase. And here's just some pictures of diffraction. Here's another picture of water waves being made from two faucets. And one very important picture is that if you look at the waves, at the diffraction, they end up getting biggest in the middle and they tail out. You can see that in this picture here. They're brightest right in between and they tail out. And that kind of property of going very big in the middle, tailing out, very big in the middle, tailing out, that will be the hallmark of diffraction. And we'll see it later.